In this lecture video, we're going to cover two independent proportions. So we want to ask the question, is the proportion from one sample different from the proportion of another sample? And is this difference statistically significant? So we're going to test this using a z-test. And if you recall from confidence intervals and from testing for a single proportion, whenever we're dealing with proportions, we're always using a z-test. And we're also going to end up with similar requirements as well. So if we have a small sample size, then we need to make sure that we're pulling our simple random sample from a normal population to independent samples from two normal populations. And if the sample sizes are both large, then we don't really care about the populations being normal. And for us, large means that NP and NQ are greater than or equal to 10. So again, we've checked for this before when we did confidence intervals for proportions, and we've also checked for this when we did a single proportion hypothesis test. So our random variable is going to be the difference of proportions, and it's per the central limit theorem going to follow a normal distribution. So we're going to need to compute a couple of things, and as usual, Excel is going to compute them for us, but we're going to need to know the pooled proportion. So let's define really quickly what all of these little letters and subscripts mean. So we have PC is the pooled proportion. And you're going to have two populations. You're going to have population A, and you're going to have population B. You could think of this as population 1, population 2, however you want to label them. But for this notation, we're using A and B. So X sub A is the number of successes from sample A. So sample A is just a sample from population A. And then XB is the number of successes from sample B. We also have NA. This is sample size A. And we have NB. And what we're really looking at is the sample proportion. So we're going to have P hat A, or you could think of it as P prime A. It's just the sample proportion from A. So it's just the number of successes over the total number of your sample size, right? So, you know, if we had 100 people in sample A and 25 of them had success or said yes, or however you want to describe that, then your sample proportion is 25 out of 100 or 25%. Similarly, you're going to have PB hat or PB prime. However, I like hats. The textbook likes primes, but pick your poison. This is the sample proportion from B. And the way that you compute it is just XB, the number of successes from your sample from B, divided by the sample size from B. And we're going to compute our test statistic and our pool proportion and our standard error and all that good stuff. We're going to have Excel do that. But what we need to do is we're going to need to provide Excel with good information. So before we go through an example running through how to do that, let's figure out how we're going to set up our null hypothesis. And unsurprisingly, it's going to be really similar to how we did it for independent means, meaning that the null hypothesis is always going to be the assumption of no difference between the variables. So if PA is our true population proportion, actually, let's add that to our notation list really quickly. So PA, no hat, no prime. This is the true population proportion for population A. And then PB, no hat, no prime. This is the true population proportion for population B. This is like mu1 and mu2 or mu A and mu B, but instead of mu for means, we're using P for proportions. So when I'm stating the null hypothesis, I'm going to use that notation. Instead of mu A and mu B, I'm going to use PA and PB because we're now doing a hypothesis test on proportions, P, not means mu. So. And so since we're assuming that PA and PB are the same, you'll notice that in the computation of the z-score, this would then have to be equal to 0, right? Because if they're the same, then PA minus PB would be 0. When we're looking at PA prime minus PB prime, this is going to be the difference of our sample. So if population A has a 25% proportion sample, and if population B has a sample with, I don't know, like 27, then the difference here would be 2%. So we're comparing 2% measured difference versus 0% assumed difference. All right, so let's look at this first example here. 2 types of medication for hives are being tested to determine if there is a difference in the proportions of adult patient reactions. And what we're going to look at is who still had hives after 30 minutes from taking the medication. So I'm going to call this first one, I'm going to call this population A, and I'm going to call this population B here. Okay, so for population A, we have some information we can dig out. Namely, 20 out of a random sample of 200 adults still had hives. So as far as the number of people who said, yes, I still have hives, that was 20. And my sample size was 200. So in order to compute my sample proportion, PA hat, it's just going to be 20 out of 200. For population B, the number of successes I had, meaning, and unfortunately in this case, number of successes is the number of people who still had hives, because you're asking a yes, no question, right? It has that binomial field that the central limit theorem turns into a normal distribution. So this is 12 people said, yes, I still have hives. Out of how many people did we ask total? 200. And so then the sample proportion from B is just 12 out of 200. So you can definitely convert these into decimals. If you want to do that before starting Excel, you're welcome to. However, you can just type in 20 out of 200 and 12 out of 200 into Excel. We need a significance level. So we see here that we have 1% level of significance. Okay, so I've got alpha equals 0.01, which is the same as 1%. And then I want to set up my null and alternative hypotheses, because while I know that my null is always the assumption of no difference between the populations, I need to understand how the alternative hypothesis is structured in order to figure out, is this left tail, is this right tail, or is this two-tailed? So going back to the question, I look at the first sentence and it says, if there is a difference, and that to me is the tip off that we're going to use not equals to. So when I'm looking at my alternative hypothesis, I'm going to have PA not equal to PB, and this is telling us to use a two-tailed test. All right, so let's go ahead and put this into Excel and see what we get. So in Excel, when you have a z-test for two proportions, it's not going to ask you XA or XB. It's not going to ask you for the number of successes. It's going to ask you just straight up for your sample proportion. So for you, it's asking you for your p hats for A and B. So this is going to be 20 yeses out of 200 total, and your sample size was 200. Your sample proportion for the second population, that was when you had 12 people with still having hives out of 200. So that gives you your 6%, and your sample size was also 200. You do not need to have the same sample size when you're testing for independent proportions, nor when you're testing for independent means. So it's nice that I had 200 and 200, but it very easily could have worked if I had 200 and 150. They don't need to match. The next thing that we need to put in, because you'll notice we have some alerts over here on the right-hand side, I need to put in a significance level. And we said that our significance level here was 1%. So I need to put in 0.01. And when I do that, I can also get a confidence interval to spit out as well, if you're ever asked for such a thing. Okay, so let's grab that and bring it back to OneNote. All right, so we put in our data. And we can actually, let's look at the confidence interval really quickly. So again, kind of just harkening back to module 3 confidence intervals, or even thinking back to when we had our z-test for a single proportion, you can definitely think of it in terms of a confidence interval. And I'm just going to say this really hand wavy and loosely. Notice that the confidence interval that we created at the bottom left of the screen, we captured the 0. So we don't find that 0, meaning like P1 equals P2, or rather that P1 minus P2 is 0. We don't find that to be too odd. That ended up in our confidence interval. So it's not like this crazy weird out in the boons, out in the tails thing. So my first thought is, I probably won't be able to reject the null hypothesis because the confidence interval I created based on our sample captured the 0. However, you want to be more formal with it. So let's just go to the p-values. We know we're doing a two-tailed test. So we can look at our p-value that's two-tailed. And as always, we're going to compare that to alpha. So what we have here is our p-value, which was two-tailed, being 0.14037, and then comparing that to alpha, which was just 1%, we can definitely see that our p-value is much larger, hence we fail to reject. Right, so we can't say that we have evidence to say that like the proportions are actually different. We're kind of just like, oh, okay, well, I guess you could be right. that's the long and short of it. All right, so let's look at one more. They all kind of go the same. You have two proportions, you have to decide left, right, or two-tailed, you plug everything in. Hey, here's my p-value, whoop-de-doo, reject or fail to reject. So in this particular example from OpenStax, a cell phone company claimed that iPhone smartphones are more popular with white people, non-Hispanic, than with African Americans. And then they conduct this study of smartphone use among adults, and they get these results. So before we kind of set up our null and alternative, let's just digest the information. So we're going to have population 1. I'm going to call this first bullet point. You can be 1 and you can be 2, right? So we have XA and A and PA hat, right? So XA is the number of yeses, NA is the sample size, and PA hat is the sample proportion. So if I'm reading this first bullet point, the results of the survey indicate that of the 232 African-American cell phone owners, that's telling me sample size, 232. And then it says 5% of them had an iPhone. So I can go over here and I can put 0.05 for 5%. Now, if you think about what's in Excel, I only need NA and the sample proportion. 232, and 0.05. I don't need to know the number of yeses. I just had that in the first one because I actually had to compute the sample proportion, 20 out of 200. I wasn't given a percentage. I had to compute it myself. In this case, they're just giving you the percentage. Thank you, OpenStax. Save me the trip. And for population 2, it's going to be the same thing. They're not going to give you your number of successes from, okay, I just realized these should be ones. And from population 2, it's the same story. Right? They're not going to give me the number of successes. They give me the sample size, which is 1343, and then they give me the sample proportion, which is 10% or 0.10. We want to test at the 5% level of significance, right? That's given over here. If they don't give you level of significance, just use 5% as always. All right, we know the null hypothesis is always the assumption of no difference between variables, i.e. the proportions are the same for both populations. Now, what are we testing? Cell phone company claimed that the iPhone smartphones are more popular with white people than with African Americans. And so that's what they're trying to show. So population 1, they're saying should be smaller. So it should be like this, right? The proportion of population 2 should be higher than the proportion of population 1. And so that tells us that we're going to do a left tail test. And now that we have all this information, we're ready to plug it into Excel. All right, so once we plug in our values, you can see that I plugged in my sample proportions as given for P1, P2, and then my sample size as given for N1 and N2, and those are here. I gave it the appropriate significance level. It constructed the confidence interval at the bottom based on the sample of a difference of 5%. And you can see that based on this confidence interval, we didn't capture the 0. The 0 is not in this interval. So that leads me to think, oh, okay, I'm probably going to have to reject the null hypothesis. Like I didn't capture the 0, so the null hypothesis isn't in there. So I'm probably going to reject it. Let's see. We know we're looking at a left tail test. So for a left tail test, that's over here. And behold, I indeed will reject the null hypothesis. So I've got my p-value for a left tail. That was 0.00764. Comparing that to alpha at 0.05 or 5%, you can definitely see p-value is smaller. So you're going to reject the null hypothesis. Rejecting the idea that there's no difference because you have some pretty compelling evidence that in fact the proportions are different. You have evidence to support the claim that white people have a higher proportion of usage of iPhone than African Americans per the context of the problem.